No, va bene,
So, good afternoon. Today we conclude, I hope, the course, meaning that today we close up all the topics which were planned for this course, hopefully, which means that the remaining lessons, meaning tomorrow and lessons of next week, they will be dedicated to do some exercises, okay, just in preparation for the final exam. Okay. So the last topic which we have to cover today is the one you see in the slide, which is RFID collision arbitration. So the usual summary, wrap up of what we have seen so far in the field of RFIDs. We have seen last time that these systems are basically sensor networks. They're similar to sensor networks, with the only main difference that sensors in RFID systems, they most likely do not have batteries, they do not have power supply, which means that all the transmission and, as you will see today, collision arbitration protocols should be accomplished through energy scavenging, so through just getting energy out of external sources. And these external sources are, as we have seen last time, provided by the reader, which is the object, let's say the central coordinator of any RFID system, which besides other stuff, it also provides energy to their RFID tags. We have seen that there are a couple of ways this energy provision and energy scavenging can be accomplished. We have spoken of near field coupling and far field coupling, so two ways how this coupling, this energy provision can happen. And basically we have stopped here last time on the problem of collision arbitration. Okay, so today what we will do will be first to define the problem and then to see what kind of protocols can actually be used to solve this problem. Okay? So let's see what the problem is. So the main goal, the main target of any RFID system is basically identification, as the name says. So any RFID system is out there to identify things. And these things to be identified are these RFID tags, what we have called sensor nodes in active wire sensor networks. This identification task is usually composed of two different phases. The first one is the phase of interrogation. Shall I use the microphone? Can you hear me? Yes? Can you hear me? No? Let me use the microphone. So as I was saying, this identification task is composed of two phases. The first one is the interrogation, which is the, let's say, most naive phase where the reader, there on the left, just sends out some kind of interrogation message to the tags. This message is used, let's say, with two purposes. The first one is to first provide energy to the tags, because this is all passive, right? And the second one, with this energy which is provided, the tags shall respond to this interrogation. So the second phase of identification is the response from the tags to the reader. Tags is a kind of synonym of RFID sensor node. So it's a tiny thing which is then used to identify things. Okay. So what the problem is here is that for each single interrogation message which is sent out by the reader, okay, since most likely the number of the tags which is to be identified is higher than 1, okay, all the responses which should get back from the tags to the reader, okay, are multiple, which means that the reader in this case has a problem of discriminating between or among multiple responses, multiple concurrent responses which are coming from multiple tags which have to be identified. Okay? And as you teach me, in all the cases where I have multiple responses, multiple messages which are actually using the same channel, I have a problem of collisions, okay? Or I might have a problem of collisions, and in turn, this means that I have to design some kind of collision avoidance mechanism, or some kind of mechanism which somehow is able to take care of collisions. Meaning, whenever a message is collided, the message should be retransmitted. Okay? And in the field of RFID system, this process is called collision arbitration, or simply arbitration. So the arbitration is basically the process in which multiple concurrent transmissions from multiple concurrent tags are actually resolved. Where resolved means all the tags are correctly received by the reader. Okay? Clear? So, if you stop thinking for 1 second, this kind of problem is kind of similar to the problem of classical access control, where you have a shared resource, a channel, which is shared among multiple transmitters, and then you have to design some kind of protocols to manage the medium access control, so the access to the shared medium, okay, in such a way that the efficiency of the overall process is maximized. Okay, so this is, if you think of it, more or less the same stuff. I have multiple transmissions which need to share the same channel. Okay, which are the differences though? There are the ones which are listed in the slide. The first one is let's say, in classical medium access control problems, you don't really have any, or in most of the cases, you don't really have an a priori knowledge on how many tags are there, how many transmitters are there. Transmitters just, kick in the network, they start transmitting, they start doing traffic, then they may go and come as they wish. So there is a kind of high dynamicity, I hope it's the right word, but I guess you understand it, right? So time varying structure of transmitters, such that transmitters may change over time, in a sense. In RFID system, that's not really the situation, because in RFID system, what I have is usually a fixed number of transmitters, which is the number of tags which I want to resolve. The point is that this number is unknown to the reader, or in some RFID application, it is unknown to the reader. Okay, so in classical medium access control program, I have an unknown time varying pattern of traffic. In RFID system, I have an unknown fixed number of transmitters. Okay. Second difference is that I have a central point here. Sorry, let me rephrase it. I must have a central point in RFID systems. Because I must have the reader which provides energy to the task. Which means, as we will see, that in RFID system, maybe it's a good idea to have centralized kind of arbitration control mechanism, rather than distributed ones. Because I already have this central point, why not use it in some wise way? The third difference is the second bullet here. Tags are even more resource constrained than typical sensor nodes, which means that they cannot run any complex or heavy medium access control protocol. For example, carrier sensing there is out of the picture. So 15.4, 82.15.4, just to name one, okay, cannot be implemented on passive kind of hardware. Because carrier sensing, why not? You tell me. Why can't we implement carrier sensing on passive hardware? Because carrier sensing is based on a continuous monitoring of the carrier, the channel, right? And continuously monitoring the channel, it means that the receiver must be on continuously. Okay? We have said 2 seconds before that this is passive hardware, which means that it's activated only by readers, which means that carrier sensors cannot actually be continuously on those nodes. Okay? So we really need to find different kind of approaches to solve this same problem. Okay? Let's see what kind of solutions are actually implemented. As you will see, it is true that collision arbitration is different than medium access control, classical medium access control, but we will see that some of the most deployed solutions to collision arbitration are actually based on classical medium access control protocols, properly modified, let's say. And what you see in this slide is actually a classification of different approaches to solve this collision arbitration mechanism. The first one, so the first classification is a vertical one, which basically distinguishes the different approaches depending on the type of protocol which is used, or the family of protocols which are used. And as you can see, according to this classification, we have basically 2 families of protocols which are implemented in real RFID systems. The first one is aloha-like access control or collision arbitration protocols, which are based on slotted aloha, which I guess you're familiar with from other courses. And more in details, they're based on some version of the slotted aloha, which is called dynamic frame aloha, which I guess you have not seen. Or did you? Did you see it somewhere else? No. Yes, no? Slotted aloha, yes. Frame aloha? Yes? Which course?
Rete di comunicazione internet.
Con chi? With whom?
Filippini.
That's very strange. Anyhow. And the second family is the family of protocols which are based on search trees. So it's data structure which are then used to efficiently search and solve collisions based on this graph structure which are trees. Okay? And we will see examples belonging to the 2 classes in the field of RFID systems. The second classification is based on more, let's say, horizontal features of a specific approach, meaning that depending, regardless that you're using, for example, an aloha-like approach or a binary search approach, you can implement it in a centralized or a distributed way. So, second classification is really how the 2 aforementioned protocols are implemented in practice. Centralized in a centralized way, in a distributed way. Or, what type of channel feedback do you have when implementing, for example, dynamic frame aloha or binary search tree? Okay? Example of channel feedback is basically what is the status of a transmission which was performed in the previous slot. The transmission could have been, for example, successful, collided, or not performed at all. Okay? So depending on the type of information you have out of a transmission, you have a feedback which is binary, for example, if you have just successful or collided, or ternary, as in this case, if you can also distinguish between transmission and non-transmission. Okay? Clear? So the solutions which are out there to solve the collision arbitration are actually a mixture of these 2 different classifications. What I mean is that there are solutions which are based on aloha, which exploit, for example, ternary feedback, solutions which are based on aloha, which exploit binary feedback, and so on and so forth. Okay? Clear? Questions? Okay, so let's first define what our performance target is. In this specific case, the performance target, which is also called the efficiency of the collision arbitration, is defined as, I would say, the time taken by the collision arbitration protocol to solve all the tags. And by solve all the tags, I mean by receiving one message successfully from all the tags. Okay? So, this is a kind of recurrent formula in the sense that we will use it, I guess, today very often. So let's stop here for 1 second. So this efficiency, which is defined as eta, okay, is defined as the population, so the number of tags which is to be resolved, big N, which, just to remind you, it's a fixed number but unknown number. We don't know it in advance. Okay? And what we have down here is a time measure, it's temporal measure, let's say. So it's the time taken to solve all these big N tags. This can be measured, for example, in number of slots which are taken to resolve these N tags, or it can be measured in seconds and so on and so forth. Okay? Clear? So, what's the ideal case? Suppose that we measure here the L of N parameter in number of slots. Okay, so our goal is to design a system whose efficiency is as close as possible to 1. Because if this efficiency eta is 1, it means that to get N transmission correctly, I only need N slots, which is the minimum one. Okay? So with this definition, okay, I expect to have efficiency of practical protocols which is lower than 1. Okay? Questions? Is it the same stuff Filippini did or not? Yes? More or less. I have to ask him why he did so.
I said this because if you use the binary tree, we have after any group, you have to skip one time as well.
Say again?
I said yes and no because if you use binary tree to arbitrate, we have to skip after any group one slot empty. I'll start everything.
Okay, I mean, the main reason, the most naive reason is that you cannot have 2 transmissions in 1 slot, right? So the minimum number of slots you need to solve to have N transmission successful is N. Then, if you are using any kind of protocol, you are even increasing the number of slots you need because you have overhead, for example, in binary tree or whatever. So again, any kind of protocol which I'm showing to you today as an efficiency defined like this, which is strictly lower than 1. Okay, no one achieves 1 as efficiency. Lower, strictly lower. Okay. Questions? Okay, so let's have a look at these protocols. We'll start from aloha-like protocols. Since I guess that you already have this background, I will go very quickly through the slotted aloha, which is the main building block of these protocols. If anyone has any doubt on the slotted aloha, just raise your hand and I'll stop there and be more precise. Okay? To move to frame aloha, which is something which I guess it's more newer to you. Okay? So let's talk briefly about the slotted aloha. So what's the assumption in slotted aloha? Slotted aloha does not use any channel feedback, which means that the channel feedback which is used is only whether the transmission was successful or not. It's based on acknowledgement. Okay? The protocol is very simple and stupid. Time is locked, as the name says, which means that time is divided into chunks which are equal. Okay? And according to the protocol, anyone who has a packet to be sent, okay, just send it in the first slot which is available. Okay, so it's kind of try as you can approach where you just have a packet and you just send it straight away, the first available slot. Then, since you can collide, which means if the acknowledgement does not come back, you have to somehow randomize the transmission. Okay? And there are several ways this randomization can happen. For example, through backoff or these kind of approaches. So it's a very, very simple and stupid protocol, which is though one of the most used in its pure format or in variation in real systems. Okay? So in this case, for example, I have two nodes which are sending a packet at in the very same time slot, the green node and the light blue node. Okay? There's a collision, which means that these two nodes do not receive an acknowledgement in some next slot, which means that they have to retransmit their packets randomly in the future. In this case, node A, the green one, will randomize such that the next attempt is here. The blue one will randomize such that the next attempt will be in some consecutive slot, which means that in the next transmission, they will not experience any collision. Okay? So in slotted aloha, I can collide the first time, but then the probability that I keep on colliding is lower and lower as I keep on colliding. Okay? I'm sure you have seen this performance model of aloha, so let me go very quickly through it, or better, let's get to the final model. So what this model basically represents is the channel traffic, so what is the throughput of a slotted aloha system as a function of the incoming traffic. So what you see in this slide, in the following slide, is actually two parameters. The first one is G, big G, which is the incoming traffic, so the traffic on the channel. And the other parameter is S, which is the throughput. So how much of this traffic on the channel goes through successfully. Okay? And under different assumptions, which I'm just skipping here, you can easily show that the throughput of any slotted aloha system, which is defined as S, is equal to the channel traffic, so what you offer to the channel, which is called big G, okay, multiplied by a number, which is e to the minus g, which is basically the success probability. So the probability that one single transmission implementing slotted aloha goes through the channel. Okay? And you can show that this probability has this exponential form because you are using Poisson traffic and such. But I guess this is something you have just seen in other courses, like in wireless network, for example. True? Okay. What is the point here? The point is that slotted aloha is very nice because it's very simple to implement. However, it has one fundamental drawback, which is that it's not stable. In the sense that if you plot the throughput versus the channel traffic, you see that this throughput has a maximum, okay, which corresponds to a given amount of incoming traffic. But then if the traffic goes on, the throughput goes to zero. Okay? Which means that, fine, it's a very nice and simple protocol, but it's not stable, which means that if we are not able to control the traffic, we're going to get a throughput which is zero. Okay? Clear? Okay, so what I did was to build on top of this slotted aloha idea to come out with more refined protocols which were then reused in the field of RFID systems. Okay? And one of these more refined protocols is called the frame aloha. Again, it's an extension of the aloha protocol, where the main difference is that the, let's say, time dimension in frame aloha is subdivided into frames, as the name says. And the idea is that basically all the tags or nodes which take part in the access procedure, they have to randomly choose one slot in one single frame, and if they go through, fine, which means that they are solved in the RFID jargon. If they do not go through, which means that if two nodes choose the same slot, for example, in the frame, these two nodes, these two tags, have to redo the process in consecutive frames. Example. This is a temporal axis. The long bars here are the frame delimiters. Okay, so this one is the first frame. Then I have the second frame, the third frame, and so on and so forth. And in this case, I have a bunch of nodes which are running the frame aloha protocol. And for example, one node is choosing the second slot for transmission. This is the only one, so it goes through. Then some nodes choose the fourth slot, the blue one here, for transmission. Since there are more than one, there is a collision here, which means that in the next frame, the node which collided this slot, they will have to do the same thing again. So they will have to choose another slot in all the slots of the frame. For example, in this specific case, I have a collision of 3 nodes here. Then one of the 3 nodes is choosing the third slot, and it goes through the second frame. The other 2 choose, unluckily, another time the same slot, which is the 5th one or the 6th one here, which means that they will have to redo the process again and again until they get solved, which means that they choose 2 slots which are different. Okay? Clear? Questions? So, the rules of the protocol are, I have a frame until you're not resolved, which means until your transmission has not gone through yet, you keep choosing randomly one slot in each frame. Okay? Questions? Okay, so let's see what the performance is of this kind of approach. And let's use the same performance metric as, what do you call it? We have defined before, so the efficiency of the collision arbitration process. Okay? So the first thing we have to calculate to get to that measure is what is the throughput of a frame aloha approach. And to do that, we start off considering the frame aloha on a single frame basis. So we just focus on, for example, one frame, the first one frame of the previous slide here. So just considering that there's no future, there's only the first frame there. Okay? And we ask ourselves what is the average throughput under frame aloha on a single frame. So basically, the throughput we want to measure is the average number of successful transmissions which go through one single frame. Here. And this is what is represented as expected value of S, so the expected value of the throughput S, average number of transmissions, okay, which is given by that formula there. In that formula, what you see is small n is the number of tags which take part into the process, and small r is frame size, so how many slots are in the frame. Okay? And that value there exactly gives you what's the average number of successful transmissions which happen in a frame of dimension r out of a population of n tags, nodes or whatever, given that these n nodes implement the frame aloha protocol. Okay? Is it clear, this function here? So it's very easy. So, suppose you have a frame of a given number of slots, right? From 1 to R. Okay, and suppose we focus on one single tag and on one single slot. I ask you, what is the probability that a tag which is transmitting in slot 1, Okay, it goes through. What is this probability? Huh? It's what? The probability that this tag is choosing slot 1, right? Which is 1 over R. That's the probability that this guy is actually transmitting here. Okay? I want to know what's the probability that this tag is the only one transmitting there. I have to multiply this probability by the probability that all the other tags choose another slot. Okay? Which is basically 1 minus 1 over R, okay, to the power of n minus 1. Here, so this is the probability that tag I successfully transmits in slot 1. Here. Then, since I'm interested in the average number of transmission out of all the tags, out of all the available slots, I have to multiply this stuff here times R, because this tag I can actually choose uniformly any of the R slots in the frame. Okay? And then I have n tags in my systems, which means that I have to multiply all this stuff by n, which is the number of tags I have in the system. Clear? And this is actually the average number of transmissions which are successful out of all the n tags in my system, and given that the frame size is R slots, which is exactly what is written out there. The assumption is that all the slots, sorry, all the tags choose randomly one slot in the R slots in the frame. That's why all the stuff is independent. Clear? So what is the efficiency? The efficiency is, as we defined it, is basically how many successful transmissions we have, since we are constrained on a single frame basis, is the number of successful transmission over the total number of slots we have in our frame. Again, if everything were ideal, this efficiency would have been 1. However, since we cannot have this ideal condition, the efficiency is given by the ratio, which is the expected number of successful transmission in the frame over the R slots in the frame itself. Okay? Which is given by this formula here. Questions? I'm just dividing formula up there by R again, which is the number, sorry, the frame size, number of slots. So if you take this expression of efficiency, again, number of successful transmission, or better, number of slots which are used for successful transmission over entire number of slots, if you study this expression, what it comes out is that there is a maximum value for this efficiency, which is when the number of slots in the frame, so the parameter R, or the variable R, is equal to the population size. So is equal to the number of tags which are there, which is kind of reasonable, right? So if I have a number of slots which is the same equal to the number of tags, this kind of what do you call it? This kind of setting is the one which allows you to have the highest efficiency as possible. Is it reasonable? Yes? No? So what's the trade-off here? Why can't I just have a value of R which is smaller than n? What do I lose there? So what is the trade-off? If there is a maximum or a minimum of a function, it means that there is a trade-off, right? In any case. What I'm telling you is that the maximum value of this eta efficiency parameter is when n is equal to r. Or better, r is equal to n. What if I set r much smaller than n? What happens? Where do I lose? Huh? If r is much lower than n, it means that I have, I'm losing in the numerator of that expression, right? So I'm losing in the average number of successful transmissions, which is going to be very low, right? What if I set r much higher than n? Where do I lose?
The efficiency is low.
Why?
Because we have inside the frame.
Right, so I'm losing in the denominator of that expression, because the frame is, let's say, not proportional to the population which I want to resolve, which means that I'm wasting a lot of slots, which most likely are going to be empty, okay? Which is again overhead. Clear? So that's why there is this optimum value, which is basically when r is equal to n. So when the number of slots is equal to the number of tags in the frame. It's the same stuff Filippini told you, yes? Yes? It's the same thing you studied with Filippini? Exactly the same stuff, same slides. He stole my slides. Good. Huh? Identical. That's it's a plagiarism kind of good. Or maybe it's the other way around. I stole Filippini's line. You'll never know.
Copyright?
Huh?
We have copyright?
No. It's a friend of mine, so no. Okay. So, what is the problem? The problem is that the process of arbitration must be dynamic, which means that I don't really need, it's not enough for me to have just one single frame, which means that I really want to solve all the tags. So I cannot afford to have any tag which is not resolved in any RFID system. Okay? Which means that the frame aloha must be implemented across consecutive frames, multiple consecutive frames. So I have to keep on doing the frame aloha process until all the tags are resolved somehow. Okay? In the multi-frame frame aloha, there is another problem there. The problem is that basically, as you go on implementing the arbitration resolution process, the population, which is still remaining to be resolved, decreases, right? So you start with 10 tags, for example. After the first frame, you have recognized 2 of those, which means that you have 8 remaining tags. You do the same stuff, you recognize 3, so you have 5, and so on and so forth. Which means that at every consecutive frame, you have a new population of tags which are still unresolved. Okay? Why is this the problem? Because as I've showed you in the previous slide, there is an optimum frame size which depends on the population size. Which means that in current frame aloha implementation, what I have to do, besides running the frame aloha protocol frame per frame, is also to modify the frame size at every iteration. Clear? Such that most likely the current frame size is equal to the so-called backlog of not resolved tags. Why so? Because this is the optimal choice on single frame, on a single frame shot. Okay? So the process is basically the same as I told you before, with this tiny difference that I just modify the current frame size depending on where I am in time. So for example, here I'm starting with a frame of, I don't know how many, 10 slots. Then I recognize 2 tags, which means that I have modified frame to make it shorter. Then I recognize another tag here, which means that the new frame is going to be shorter, and so on and so forth. Within the same frame, the rules are always the same. So every node which is not resolved, it keeps choosing randomly one slot in that frame until it gets resolved. Okay? Clear? So basically, the efficiency of multi-frame aloha depends as the efficiency of the single frame aloha on a parameter n, which is the initial, let's say, population. And it also depends on the current backlog. So basically, how many tags are resolved at each step of the resolution process. Okay? So, unfortunately, there's no, let's say, clause for the efficiency of multi-frame aloha. But luckily, there is an iterative formula which tells you how the efficiency of the multi-frame aloha can be actually calculated. Okay? Which is the one you see in the slide. So efficiency is always eta ratio between number of initial tags over the duration of the arbitration phase, L of n. So what we have to find is what is this L of n. So what is the size of the overall arbitration process, which is taken by the multi-frame aloha. Okay? And this is the formula which tells you let's say, recursive formula which tells you how this L of n parameter can be calculated in the field of multi-frame aloha. Let's have a look at it in more details. So this formula is telling you that the entire arbitration process takes you R slots, which is the initial frame, okay? So the size of the initial frame, which you have to pay. And then it takes an additional number of slots, which comes out from a probability distribution. So it depends basically on how many tags were resolved at the previous steps. Okay? So if you have a look at this sum here, you are starting with n tags in your system. That's the initial population. Okay? And then you're saying that you have to sum up the slots of the first frame, okay, with the number of slots, which is L to the n minus I, weighted by the probability that in the previous step you solved actually I tags. So if you just disregard the sum sign here, okay, this product here is the probability that at the previous frame you solved I tags, which means that you had high successful transmissions. And then if you had high successful transmission, it means that you have a new backlog, which is n minus I. So you still need to resolve n minus I tags. Okay? And that's where the recursion is. Clear? Questions? Then, if you just do some maths out of this formula, which means, for example, you're just taking out of this formula the probability of non-solving any tag, so the probability that S is equal to 0. If you move out of this summation, the probability that S is equal to 0, okay, which is multiplied by L of n, which is exactly the same as here, and then you just move this stuff on the left-hand side. What you can write down is a new formula, which is totally equivalent to this one, which is again just this formula here, where I've moved out the summation, the term where I is equal to 0. Clear? Questions? And then, once you have this formula, you can actually calculate with the recursion what is the duration of the arbitration phase. Let's see an example, maybe. So let's see this example here, which is very simple, just to see how things are actually running. Where I have two nodes, two tags. So n is equal to 2. N is the initial population. Okay? And R is equal to 2, which means that the initial frame size is equal to 2. What I want to find is L of 2, okay, which is the duration of the collision arbitration process with 2 initial tags. Okay? So what I do is just to apply the previous formula. So L is equal to 2, this one here. I just change the names with the numbers. R is 2 in our case, N is 2 in our case. Okay? And what I get is what you see written here. L of 2 is equal to 2, which is the size of the initial frame, plus this sum from 0 to 1 of this weighted sum of the L of n values there. Okay? In this case, I'm lucky because the term to sum are not very many. It's just 2 of those, which is the probability that in the previous frame I did not solve any tag, which is P of S equal to 0. And the probability that in the previous frame I just solved one of the 2 tags. So P of S equal to 1. Okay? Which is what I've written here. So this is basically the explosion of that summation of only 2 terms. Clear? Questions? Then what I can do is just to modify slightly the formula like this, meaning I just group up the L of 2 terms at the right hand side of the equals and at the left hand side of the equals, okay? And which means that I have at the denominator this term here, which is 1 minus P of S equal to 0. Clear? Okay, and then this magically gives us 4. Why is 4? So you tell me, in this case, what is P of S equal to 1? What is it? This is equal to P S equal to 1, which is here. This is the probability that the previous step I solved just one time. So I had just one successful transmission. What is it? Let me remind you what the system is. Our system is composed of 2 tags and 2 slots. Okay, so this is my frame with 2 slots. This is slot 1 and this is slot 2. And my initial tags were 2. What I'm asking you is what is the probability that in this setting I have just one tag which is successfully received or translated successfully towards the ring. What is it? So you just have to run the frame aloha in single frame, which is very simple in this case, just 2 slots. And you have to ask yourself what's the probability that only one tag is resolved. What is it? Exactly. It's impossible. So in this setting, it's impossible that only one tag is correctly received. Because either both tags are received, so one chooses slot 1, the other one 2, and vice versa, or 0 tags are resolved. So they both choose the same slot. Either slot 1 or slot 2. Okay? So this PS equal to 1 there is 0. So at the numerator there, you have only 2 over something. Okay? What is PS equals 0? PS equals 0 is the probability that no one of the 2 tags is resolved. Which means it's the probability that the 2 tags, they both choose the same slot. What is it? What is it? Huh? 1? 1 up, right? Because they can choose they both can choose the first slot, which happens with probability 1/2 times 1/2. Or they can both choose the second slot, okay, to collide, which again happens with probability 1/2 times 1/2. Okay? So this PS0 there is 1. So if you put into here 1/2 and up there 0, what it comes out is that it's 2/1/2, which is 4. Okay? 4 means that on average you need 4 slots to solve 2 tasks running frame aloha, multiple frames. Okay? Which means that what's the efficiency? The efficiency is the ratio between the initial population, which is 2, over this value which we have found, L of 2, which is 4, which is 1/2. Okay? So the efficiency of multi-frame frame aloha in this case is only 50%. Which means that 50% of the slots are just wasting. The other ones are the ones which on average contain successful transmissions. Clear? Questions? And then you can, for example, run some other examples just by increasing the number of tags or the number of slots in the initial frame and so on. Questions? Clear how to apply this formula? Good. Same question as before. Filippini? What about Filippini? Good. So this is very fine, very nice. It's very nice because we have, let's say, clear dimensioning formulas to properly set our frame aloha-based system. There's only one missing problem, which is, though, kind of important. And the problem is that in most of the cases, the initial population is not known. So the parameter n, this parameter here, which we have assumed to be equal to 2 in this case, which is the initial number of tags to be read, okay, is not known. Because in most of the cases, it's exactly the outcome of the RFID process, of the identification process. I want to know how many pens are in my box, for example. I want to know how many items are on my shelf, which is exactly to, let's say, estimate or to get out of the RFID system how big is this n parameter. So the n, big N, is not known a priori in most of the cases. In some cases it is, but it's very particular RFID applications. So why is the problem? It's a problem because we really don't know what is the current backlog of tasks to be resolved, which is then the information which is used by the frame aloha to properly set the frame length, frame size. So if you don't know the initial population, you don't know how many tasks are in the backlog, so still remain to be resolved. Okay? You have some uncertainty on this parameter, which means that when you have to set your frame size at all the iteration of the frame aloha, you have to do that just by estimating the current backlog. So you don't have the precise information on what the current backlog is. Okay? Clear? Which means that efficiency-wise, it's an additional efficiency loss because you don't have the perfect information on what is the current backlog, which means that you have to guess it somehow, or estimate it somehow, which means that it's a suboptimal kind of process, which means that you're losing efficiency, most likely. Okay? So, tag arbitration is actually composed of 2 blocks. The first one is what we have discussed so far. Is basically the arbitration process. So how all the tags of the system choose one slot in the frame and so on and so forth. Okay? And how they do it across multiple frames. The second building block is a so-called backlog estimate, which is actually providing to the frame aloha block on what is the current estimate of the current backlog, which is then used to properly set the frame size. So there are 2 building blocks which basically feeds in one another information. Okay? This backlog estimate, to be more precise, is actually giving out, spitting out, and giving down to the dynamic frame aloha protocol this estimate of the current backlog. That's why it's called NEST. Okay. And then this frame aloha protocol is doing the same stuff I just discussed to you in the previous slide by setting the current frame size to be equal to this NEST, estimate value of current backlog. Okay. So why this is challenging? It's challenging because this block here has no information on the initial population, which means that it has to run based on information which is coming only from the observed responses from tags. So it's just running on responses which are received on the channel, okay, without any a priori information. Clear? So one of the most used estimates, so one of the most used implementation of this block here, okay, it's rather simple, and it's actually, I guess it's more or less the only one used in the field of RFID systems. It's called the Schute estimates, after Schute, he's a kind of researcher. Let's start from the outcome, what this estimate is. Okay. The estimate is the following. What the Schute estimates is the following. This block here, let me go back one slide. This block here just observes one frame of responses from tags, right? And it can distinguish between slots which were collided versus slots which were successful. So successful means slots that contain successful transmissions. By the way, this block is actually implemented in the reader. Okay, so the reader is actually able to read all this information. So what Schute estimate tells is to count up the number of slots which were collided in one frame, okay, and multiply the number of collided slots by this magic number, which is 2.39. Round it up, okay, and that is my estimate for the current backlog, so the remaining number of tags which still need to be resolved. Okay, so that's the outcome. Let's see how Schute got to this result here. Okay, so the outcome is fairly easy. Just count up the number of collided slots multiplied by 2.39 and round it up. And use this number, magic number, as value for your next frame size. And do it forever, basically. Okay? So basically, this estimate is built on the assumption that any estimate procedure is equal to keep the number of number of tags which still need to be resolved, which means the backlog, equal to the number of slots in the current frame. So that's the objective, and also the assumption. If this is correct, meaning that if the current frame size is equal to the number of to the number of tags in the backlog, it can be shown that if all these nodes tags choose randomly one slot in the frame, okay, the average traffic, if you observe one single slot in that frame, is Poisson distributed with this average here, which is 1. Clear? So the assumption is, if I'm able to set the frame size equal to the backlog, then the type of traffic which I observe in each single slot is a Poisson point process whose average is equal to 1 terminal per slot, which means that on average I have 1 terminal which is split in one slot. Okay? So, if I'm under this assumption, so the traffic in each single slot is Poisson distributed process with 1 terminal per slot, then I can calculate what is the probability, what is the number, the average number of collided terminals in a collided slot. Clear? Which is exactly this H number, which is the 2.3. Clear? So how to get to this result here? So assumption is that traffic is Poisson distributed in one slot, which means that in one slot I have this one terminal per slot average Poisson point process. Okay? What I want to find is how many paths are actually transmitted in one collided slot. Okay? Which is exactly the objective of shoe testing. Okay? So to do that, let's find what is the probability. Let me write it like this. The probability that the number of concurrent tags transmitted in one slot is equal to k, with k parameter, given that the slot is collided. So given that this n is greater or equal than 2. Clear? This is the probability that I have k transmission in one slot and the slot is collided, which means that at least I have 2 transmissions. Clear? Questions? So what is it? I can write down this expression just by using Bayes' formula, so by reversing the conditioned expression. Writing down, for example, that this is equal to the probability that I have more than 2 transmission, given that n is equal to a given number k, okay, multiplied by the probability that n is equal to k, okay, over probability that n is higher than 2. You agree? Okay, so what is this one? What's the value of this probability here? You see the probability that the number of transmission in one slot is higher than 2, given that the number of transmission in the slot is equal to k. What is it? No. This is a 0-1 function. So this is going to be 0 if k is lower than 2, right? This is going to be 1 if k is equal or higher than 2. So it's a kind of defining the range for this entire probability. So this probability is a probability defined as is correct to be only for n equal or greater than 2. Okay? What about this one? This is the probability, just erase this one. This is the probability that I have k transmission in one slot. Okay? So I can write down that, let's keep in mind this is a kind of domain-defined function. Let me write down this expression here, which is the Poisson distribution, right? So it's lambda k over k factorial a to the minus k, e to the minus k, which is this one here. Okay? And then I have to divide it by this stuff here, which is the probability that the Poisson point is higher than 2. So I can write it down like 1 minus the probability that n is equal to 0 and n is equal to 1. Okay? Which is 1 minus e to the minus lambda minus lambda to the minus lambda. Do you agree? So this stuff here is this one, and this stuff here is that one. Okay? And this function here is defined from k equal to 2 on. So from k equal to 2 to infinity. Here. So this is actually the probability to find k collided terminals in a collided slot, given that that slot is collided. So what I want to find is the average number of terminals. So how many on average I have in a collided slot. Okay? So to do that, I just have to apply the definition of, what do you call it, expected value, okay? Which means that what I have to find is actually the sum from k equal to 2 to infinity of this probability times k, the average value of that probability distribution function. Clear? So this stuff here, I can rewrite it as follows. I can just move out one, let's say fixed values, which is this expression here, and I have the sum from k equal to 2 to infinity lambda k here. I just moved out this denominator out of the summation. So if you just have a look at this stuff here, this is, if you do not consider actually the index of the indices, this is actually the definition of the average, the expected value of the Poisson distribution. It would have been a full Poisson distribution if starting from k equal to 0. Since we're starting from k equal to 2, it means that we have some missing terms. Okay? So we can write this as, again, 1 over e to the minus lambda multiplied by this stuff here, which is the average Poisson distribution, which would have been lambda if starting from 0. Okay? And I have to subtract to this average value the missing terms of this summation. Right? Which is basically the term with k equal to 0, which would have been 0. Okay? And the term with k equal to 1, which would have been, this is 1, so it's lambda e to the minus 1. Clear? And I'm done, in the sense that in our case lambda is 1, okay, by assumption, which means that I have here something like this. One over 1 minus 2 times e to the minus 1. And in here I have something like this. 1 minus e to the minus 1, which is exactly the value of h, which you find in the slide. Okay, again, this is the average number of terminals which transmit in a collided slot, given that the slot is collided. Okay, then if I know this number here, and I know the number of collided slot, I can find this estimate of how many terminals are still out there, backlog, just by multiplying this h number to the number of collided slot, which is called c in this formula, and then round it up because the frame size must be integer. Okay, it cannot be just real. Clear? And this is the estimate, which is used to define what the frame size is going to be. Okay? So it can be shown that in most of the cases, let me put it like this, which means if the initial frame size is not too far from the unknown population, it can be shown that this estimate is the optimum one. So it's the one which achieves the best efficiency in terms of parameter eta we have defined before. Okay, so even if it's very simple and stupid kind of estimate, still it's able to track down very well what the backlog of any RFID system is. Okay, clear? Questions? So this is obviously true if you don't have any prior information on the population, so on the random variable big N. If you have any additional prior information on the initial population, you can do better. So you can do much better than should estimate. So let me rephrase it. This is the best thing you can do if you don't know anything about the big N parameter, the initial unknown population. Okay? Questions? Okay. So if you don't have any questions on this aloha-like arbitration process, I'll move to the other class of arbitration protocols, which is the class based on binary trees, okay, which have some similarities to frame aloha, but still they require, let's say, different kind of signaling overhead to be actually implemented in practice. Okay. So what we see is, I guess, the most famous binary tree searching or arbitration process, whose, let's say, high-level idea is the following. So for each slot which is collided, so for each slot where there is a collision, what this protocol does is to divide the number of tags which have collided into two subgroups, okay, and then solve the collision of each one of the subgroup independently. Example, or better, general idea in a figure. So what you see here is actually a, let's say, a graphical representation of an execution of a binary tree protocol in the field of RFID systems. Just some definitions. What you see in the circles is the number of tags which are actually transmitting in that slot. For example, if you have a look at the root of this tree, there you see a 5 there. 5 is the number of tags which are actually concurrently transmitting in that slot. Okay? And then on top of the circle, you have the slot number. So the first circle there is the first slot, represents the first slot, slot 1, and it says that in that slot I have 5 tags transmitting at the same time. So I have a collision. The node is red because I have a collision. Okay? So what the binary tree does is the following. I have a slot 1 with 5 nodes colliding. So what I do is just to split up this group of 5 tags into 2 subgroups in a random way. So in this case, the algorithm is, let's say, the instance of the algorithm is splitting up the 5 tags in 2 subgroups of 2 and 3. Okay? And then these subgroups of 2 and 3, they will be resolved independently, which means that the algorithm will first resolve the collision of the subgroup of 2 tags and then move to solve the collision to the subgroup of 3 tags, or vice versa. Depends on how the algorithm is actually implemented. Okay? So in this case, it's splitting up 5 tags into 2 and 3. Okay? This group of 2 tags is assigned to the next one slot, which is slot number 2. There are still 2 tags transmitting in that slot, which means that there is a further split. Okay? The split is always binary, because this is binary search, binary tree kind of approach. So in this case, I have a collision in slot 2. The group of 2 nodes is split up. However, since split is random, okay, it happens in this case that it is splitting the group of 2 in a group of 0 nodes tags and a group of 2 tags, which is not efficient. Okay? However, it happens like that, which means that in the next slot no one will be transmitting because the next slot is assigned to the subgroup of 0 tags. The next slot again is assigned to the remaining subgroup, which is the original one. Okay? So still I have a collision. I have a collision, I do the same, which means that I split these 2 tags into 2 subgroups randomly. Okay? And in this case, I'm lucky because one subgroup is composed by singleton, so by single tags. Okay? This means that to solve this to solve this group of 2 tags, okay, I need to occupy up to the 6th slot, okay, in my transmission process. Then, once I'm done solving this first node here, this group of 2 tags, I move to what is remaining here, to the group of 3 tags. And I do the same stuff. So I have a transmission of 3 tags here in slot 7, which means that I split it up into 2 subgroups. In this case, I have a group of 1, so I'm fine in the next slot, and a group of 2, which still need to be split, okay? And which means that I need to take up to 11 slots to solve the initial 5 tags here. Clear? At least the idea. Then we'll see how this is implemented in practice. So whenever a slot is collided, you split randomly into subgroups the collision set. So the number of tags which are collided. And you keep doing that as long as you have tags which need to be resolved. Clear? Okay, so let's see how this can be implemented. Actually, there are several ways how this can be implemented. What I show you is how this is implemented in RFID standards, so in practical products which are based on binary tree in the field of RFIDs. And this is called the trigger split implementation of the binary tree protocol. So, what is needed from the tag side to run this binary tree protocol is to have a counter which is initially set to 1. Okay? And then the reader has to broadcast 2 types of messages. Okay? The first messages are the so-called trigger commands or trigger messages. Okay? These trigger commands are sent out at the very beginning of the process, which this can be somehow included in the, let's say, click message which is carried out by the reader to start the arbitration process. And also they're sent out after successful or empty slot. So whenever the reader sees either a slot with successful transmission or a slot which is empty, with no transmissions. Okay? Then, if the tags receive any of these trigger commands, the effect of the trigger command is to decrease the tag counter, okay, from the current value to the new value, which is that value minus 1. Okay? If after this decrease the current counter value is equal to 0, it means that that tag is allowed to transmit in that specific slot. So upon receiving that specific trigger command. Okay? We'll see an example in 1 second. Then the other command type is the split commands, which are the ones which are used to force the splitting. So to split up groups of colliding nodes. So the split commands are sent out after collided slot only. Okay? And what happens, what the effect is on the tags is that tags with a counter equal to 0, which they have transmitted in the previous slot, okay, they need to split, which means that they randomly choose a counter value in the field 0, 1, randomly, 50% 0, 50% 1. Whereas the tags with a counter which are greater than 0, so the tags which did not transmit in the previous slot, which was correlated 1, okay, they need to refrain, so they increase their counter by 1, which means that there is a collision which needs to be resolved beforehand, before these new tags can actually transmit. Okay? Example. Suppose we have this situation where I have 3 tags which I have to resolve using binary tree. By contract, these 3 tags A, B, and C, they will initialize the counter to 1. Okay? And then the first thing the reader does is to issue a trigger command. So what you see up there, that gray block there, is a trigger command. Okay? And what you see in this kind of part of the slide is the effect the specific command has on the counter. Okay? So the reader has issued a trigger command here. Okay? And the effect is that all the three tags which add a counter equal to 1, they will decrease the counter from 1 to 0, which means that they will actually transmit in that slot, okay, which is this slot here. Okay? There's a collision here, okay, which means that the reader has now to issue a split command. It has to split, okay, because it has, let's say, requested some responses, but no one is actually answering because it has, collided with other guys. Okay? So it issues a split command, okay, and what the split command does is on the tags to let each tag choose randomly between two values of the counter, which is 0 or 1. So in this case, for example, tags A and B, they choose 0 as a new value. Tag C chooses 1 as a new value. Okay? Since these two guys has a counter which is equal to 0, they keep on transmitting, which means that we are at this collision node here. Tags A and B. This guy here has a counter equal to 1, which means that it does nothing. It does not transmit. Okay? So we are here in this collision slot. There is a collision, which means that the reader now issues a new split command. Okay? Still, the split command has effect on the tags which were transmitting the previous slot, which means tags A and B, to let these tags choose randomly between 0 and 1. So this is a very unlucky case because after also this second split command, they keep on choosing the same slot. Sorry, they keep on choosing the same subgroup, okay, which is the counter value equal to 1. This is a split command, which means that the third tag, tag C, which was not involved in the previous transmission, what this guy does is just to increase its own counter, because it has to wait until this first collision is resolved. Okay? So these two guys has chosen the same counter, which is 1, which means that in the next slot, which is slot number 3, no one transmits, because they have chosen to wait one more time. After this empty slot, the reader issues a trigger command because the slot was empty, okay, by contract. And the effect of this trigger command is to decrease the decrease the counters of all the tags. The counters of node A and B will get to 0, which means that they will transmit here, again colliding. The counter of node C will decrease to 1, it's not 0, so it will start to just stay, let's say, idle for 1 second. Okay? So there is a collision here, which means that the reader now issues a new split command. Okay? In this case, we are lucky because node A chooses 1 as a counter value, node B chooses 0 as a counter value, which means that in the very same slot, node B is the one which is transmitting alone, so it's resolved. Node A transmits in the consecutive slot, okay, which means that it is solved here. Okay? So we have a split command, this guy is transmitting straight away, so it's a successful slot. After the successful slot, the reader issues a trigger command, slot was successful, which means that this guy decreases the counter from 1 to 0 and transmits here, tag A, and tag C decreases its counter from 2 to 1, which means that it refrains from transmitting. Tag B is out of the process because it has been resolved correctly. Okay? Then the last step is, since I have a successful transmission here, in slot number 6, the reader reissues a final, trigger command here, which means that this is a command which forces the last tag C to have a counter which goes down from 1 to 0, which means that C can now transmit in slot 7. Okay? Clear? So, if you just have in mind the rules, these rules, when commands are sent out and what's the effect on the tags, it's very easy to, correctly understand this kind of example. You just have to run the algorithm step by step. Yes?
It's not number 4, and choose the same value.
Say again?
If in a slot number 4,
even here, they actually choosing the same random number. Again, it depends. If they were to choose counter 0, okay, you would have had another, let's say, red node in slot 5, okay, and let's say if they had choose counter 1, the effect would have been the same as this one here. So you would have had a empty slot in slot 5 and then a collided slot in slot 6. So the structure in the tree is just the same just like here. Okay. Questions? So what's the efficiency here? What is the efficiency? I want a number. What is the efficiency in this case? Efficiency is number of tags over number of slots, right? It's 1/2, 50%. I have 3 tags, A, B, and C. Sorry, less than 1/2, 3/7, you're right. Yeah, so it's slightly less than 50%. Okay, it's 3/7. Questions? Okay, so as I was saying, this is one of the most common implementation of the binary tree available in RFID systems. Actually, there are, in real systems, this same implementation is somehow optimized to account for some specific situations. Okay, for example, if we take this case here, where I have a collision here, which is followed by an empty slot, this means that two guys were colliding, at least two guys were colliding here, and then I was observing an empty slot, right? Which means that in the following slot, for sure, we'll have a collision. For sure, I will have a collision. So collision happens with probability 1 in this case, okay? So the optimization consists in the fact that if I know a priori that I have a collision in one slot, there's no, let's say, reason why to issue a trigger command. I would rather split, right? So I would rather issue here a split command straight away, because I'm sure that this slot is going to be wasted in any case, because I have more than 2 guys using the same slot, more than 2 tags using the same slot. And this helps in saving a few slots in let's say, the total count of slots used to solve the process. Okay? So basically, all the refinements which you can find in practical system deal with optimizing this situation where I have empty slots following a collision slot. Okay? Here. Other kind of refinements which are not used in RFID system, but you may happen to find in other contexts, build on the idea of having different kinds of splitting. For example, why not using ternary splits? So why not just splitting up collided slots into 3 subgroups, not 2, or 4 subgroups, not 5, and so on and so forth. The thing is that also in that case there is a trade-off. Okay, and the trade-off is always dealing with the fact that to enforce the splitting into groups which are more than 2, it requires to have additional symmetry. Okay, so you don't need only one counter, 0, 1, at the tag side. You need more refined counters, and you need more refined messages from the reader side to handle multiple groups. Okay, that's why in a RFID system, what I've seen so far is only algorithms which are based on binary splitting, with these refinements which are used just to get rid of empty slots which follow collided ones. Okay? Do you have questions on this part? So as I was saying, this is not the only way to implement binary tree. You may have seen different implementations in different courses, but still this is the way how it is implemented in RFID systems. So you may want to compare what you know with this implementation, okay? Okay, so the last 2 slides or 3 slides, we are not seeing those in the course. It's just basically one specific arbitration algorithm which is used by one specific standard of RFID system. It's interesting, but not so much in the sense that it's just a way things are practically implemented. So a way, general concept which I convey to you today are actually put in practice. So if you got general concept, you are able to, let's say, read how these practical implementation are actually done, okay? So we are not covering it in this course, and it will not be part of the exam. This Q algorithm is called, okay? I'll see you tomorrow. Say again?
Next week, still we have classes?
Yeah, that's next week with exercises. So for sure on Wednesday, and depending on your needs, also on Thursdays.